Welcome to the C3 AI Digital Transformation Institute. Our mission is to attract the world's leading scientists to join in a coordinated and innovative effort to advance the digital transformation of business, government, and society. As you can see, we are a consortium of leading universities and industry, and we are funded by C3 AI to do this work. We have upcoming events including Stefano Soato, Jeff Shama, and Louis Shah in the following few weeks. And today, we will be having two speakers from Princeton University. You can see our former talks on YouTube channel, and shortly after this one, you will see this one as well. The format is a 40-minute presentation. Today, we'll have two speakers. We will then have a 15-minute Q&A. You'll be putting your questions into the Q&A box. And if you see a question you like, you can upvote it. You can put those questions in at any time, and we'll be answering them at the end. The title of today's talk is Bringing Social Distancing to Light, Architectural Interventions for COVID-19 Containment. We have two speakers. The first one is Stefana Parascho, who's an assistant professor of architecture at Princeton University. She's an architect with teaching and research in the field of computational design and robotic fabrication. She completed her doctorate at ETH in Zurich and her architectural studies at the University of Stuttgart. Her research interest lies at the intersection of design, structure, and fabrication, with a focus on fabrication-informed design. She explores computational design methods and their potential role for architectural construction, ranging from agent-based models to mathematical optimization. Her goal is to strengthen the connection between design, structure, and fabrication, and the interdisciplinary nature of architectural design through the development of accessible computational design tools. Our other speaker is Corina Tarnita, who's an associate professor in ecology and evolutionary biology and the director of the program in environmental studies at Princeton University. She was a junior fellow of the Harvard Society of Fellows and obtained her degrees in mathematics from Harvard University. She is an ESA Early Career Fellow, a Kavli Frontiers of Science Fellow of the National Academy of Sciences, and a Sloan Research Fellow. Her research is centered around the emergence of complex behavior out of simpler interactions across spatial and temporal scales. So I'm going to turn this over now to the speakers, and do remember to put your questions into the Q&A, and we'll answer them at the end.
Okay, thank you. So I took the first part of the presentation just to give you a little bit of a sense of the background that led to the current project. Stefana and I actually met only a couple of months before the pandemic started, and we managed to have one lunch together in which we discussed a little bit about what we both do, seeing how we were both interested in design and organization, and I was primarily interested in, I primarily work on biological systems, and I try to understand how small-scale interactions lead to emergent patterns and processes, and how we might be able to use those patterns to infer something about the robustness of the various systems. So I take a primarily computational but comparative approach to trying to understand how biological systems organize themselves across scales, spatio-temporal scales. So across, we ask evolutionary questions, we ask ecological questions, and we ask questions from the scale of single cells all the way to entire ecosystems. the conversation started because one of the things that is really interesting in how biological systems organize themselves is the role that architecture plays. And I'm going to give you two examples. These were two of the few that we discussed that day, and that then inspired Stefana to ask some of the questions that then led to this grant proposal. So, and to the current project. So, let's see if I can advance. Right. So one of the things that we have noticed is that architecture can amplify self-organization in biological systems. And here's a very simple and neat example, a very unexpected one that we recently uncovered in collaboration with an empirical group at the University of Rockefeller. So in ants, one of the major questions in evolutionary biology is how you get the evolution of very complex behaviors, such as the evolution of eusociality, which is the social behavior that characterizes social insects. And it's never really clear what exactly are the ingredients that have to get you over that hurdle at the beginning to make social behavior a beneficial activity, even despite the various costs that it is associated with. And what we found in these experiments was that if you take groups of ants and you start with one ant that has to take care of one larva, then you have two ants that have to take care of two larvae, and so on and so forth. And you keep increasing the group size, making sure to standardize the amount of work that each group has to do. What we find is that at first, small groups do really poorly. But as soon as they get at very, very small, at not too big, so already at group size 6 or 8, we start to see a dramatic improvement in colony growth rate. So in the fitness of the group, more so than anyone would expect with such a small group of individuals, because these individuals are very similar. They're genetically identical. They're the same size. They're the same age. They're trying to replicate the conditions of the very first groups that would have, when this kind of behavior would have originated, and yet they are able to somehow, in these small groups, get a really high boost to fitness. And one of the questions, and I mean, the major question was, how are they able to do that? What exactly happens to 6 ants that doesn't happen to 4 ants, but then doesn't actually necessarily increase too much more as you get to 12 to 18 ants? What we found both empirically and theoretically is the emergence of a rudimentary division of labor. This was extremely exciting because this means that individuals that are basically nearly identical are somehow able to spontaneously self-organize, even when there's very few of them, to create some sort of division of labor. And we call it rudimentary because compared to the kind of division of labor that we would see in very advanced or very evolved species, where you have nurses and you have foragers and you have soldiers and whatnot, this is a very simple kind of behavior. When you have 6 or 8 ants, you don't have enough of them to assign tasks to each one. Everyone does a little bit of everything. However, what they are able to do is that the rank within the colony of how much each does of every particular task stays fixed through time. So if I am more forager-like today than Stefana, even if I am going to do a bit less foraging tomorrow and she might do a little bit more nursing, I'm still going to be more forager-like. So we observed basically that in small groups, certain species can self-organize to lead to rudimentary division of labor, and this might be the key the key to give them the boost to evolve more sophisticated behaviors. The problem is that in these groups, no matter we made a very simple model, a simple threshold model to understand how they start doing the different tasks. No matter how much bigger the group got, that simple model predicted the appearance of this division of labor, but that division of labor eventually plateaued fairly quickly. We never really managed to get to much more sophisticated behaviors. On the other hand, there's been a lot of empirical work that shows that in ant colonies, there is a, not only do we see eventually much more specialized workers, but they also tend to be organized according to the architecture of the various nests. The bigger the ant group becomes, the more eventually they're going to end up having a more sophisticated architecture. And ultimately, what this shows, this is actually the inside of an ant colony. The top is at the surface. As you go down, there are various chambers. So this is a cast of the nest itself, and you find that different kinds of ants, different types of work are being done in different places. And the foragers, for instance, never get all the way down to where the larvae are and where the nurses spend most of their time. And it is not entirely clear how exactly they partition themselves. What we showed is that taking the exact same simple model that we used to discuss, that we used to show the emergence of this rudimentary division of labor in these very, very simple groups, if we then take the exact same model, but now we apply it on an architecture. So now there is interaction bias. You're more likely to interact with those who are in the same chambers that you are. And those happen to be the kinds of workers that do very similar tasks. Then that kind of interaction bias and that kind of social learning in some sense, or social mediation of your responses to the various demands can lead to dramatic boosts. So here in gray, you see that this is the kind of boost with very small group sizes. We barely get any, but we get just enough to actually allow the evolution of eusociality. But at much larger group sizes, if you have enough of this interaction bias, so if you have the architecture that allows you to interact preferentially with those who perform the same tasks as you and therefore reinforce your response for those tasks, then you can get dramatic increases in division of labor. So architecture can be really important to amplify self-organization. You can get self-organization almost for free, which is amazing, but then architecture can really help you amplify it. And the second and really fascinating, at least result that we have uncovered, is the importance of architecture to facilitate self-organization of species that do not otherwise self-organize themselves. So this is a satellite image of northwestern Tanzania. Each one of these dark spots of vegetation is actually a termite mound. I can talk more about, or rather, what happens with these termites? So each one of them is a termite colony. Why are they so distanced from their neighbors? You, I hope, can see that there is, or start to notice that there seems to be some sort of patterning. It looks a little bit like a polka dot dress. The mounds are of very similar sizes, and their neighbors are more or less equidistant, and there are about 6 of them. So this is a hexagonal pattern. This kind of patterning emerges because termite colonies cannot stand each other. They're super cooperative within the colony. They hate their neighbors. So they are constantly fighting with their neighbors. And when they're fighting with their neighbors, they're creating this distance. Large colonies are always able to kill smaller colonies, so you'll never really see size disparities. And as soon as they ultimately, when this whole process runs its course, what you find is colonies of very similar sizes, spaced as far apart as they possibly can from their neighbors, while at the same time making sure that there is no empty space because they're all competing for the very scarce resources. Now, termites do this, but because termites also degrade cellulose, they're amazing converters of nutrients, of energy. So there's always more nutrients on termite mounds. There's better moisture. It's a wonderful habitat for basically everything else. So the termites create this pattern, but then the plants grow better on termite mounds than off termite mounds. That attracts animals that are also doing better on termite mounds than off termite mounds. And then you can also see this with almost any metric. You can see it with below ground. Microbes are different. So termites are ecosystem engineers in the sense that you can really tell the difference between whether you're standing on a termite mound or off a termite mound with almost any metric that you might think of measuring. Now, the cool thing about this is that one of the results is that this allows animals that don't otherwise self-organize. So that's a termite mound with the very lush vegetation on top of it. And these are about deer-sized antelope that are eating around the termite mound. They're using it for all sorts of purposes. The exciting prediction seems to be that once the termites have created this pattern, they have created this template or this architecture for the landscape, everything else follows that pattern, and that allows the highest level of productivity. So the architecture itself, the pattern itself, creates some sort of synergistic effect. If you a previous study from 2010 said, okay, each one of them gives a boost. If each one of the termite mounds increases productivity for the whole system. But does the fact that they are spaced in this hexagonal pattern matter? Does that help in any way, or is it just an additive effect? And they showed by considering 1,000 replicates of random configurations of the same number of mounds, they showed that the hexagonal configuration was always better at increasing the productivity overall of the overall landscape. And one of the ways that it does that, we have discovered by basically scrambling the pattern, creating our own pattern and creating both regular patterns on the right-hand side and random patterns on the left-hand side, we discovered that animals preferentially spend time on the right-hand side. You can see that with the camera traps, you can see that by counting dung and so on. But animals seem to prefer a very neatly organized spatial pattern. And one of the reasons that we think this is the case, and this is work that is still in progress, is that this kind of underlying architecture, the spatial, creates the possibility for the animals themselves to space themselves apart and to reduce competition between them. So with these two ideas in mind, talking about how architecture plays an important role in biological systems is where our conversation was left sometime in the fall of 2019, and then COVID happened, and then Stefana reached out and said, maybe we should think about, how about we think about using architectural intervention to see whether that can lead to containment of COVID-19 by changing basically human behavior. So with that, I'll pass it on to her.
Thank you, Corina. I'll quickly share the screen and we'll be on my way. All right, so thanks a lot, Corina, for the nice intro into our project. I think you got it really well to the point. What I want to talk about now, before getting to the actual project, is a little bit on the background of my work and my lab, which is very, very different from what you've seen before. But yeah, bear with me. I promise it will somehow make sense at the end. So I am an assistant professor at Princeton University. I am an architect and I work in the School of Architecture, where I run the CREATE laboratory at Princeton. The name stands for Computational Robotics, Enabling Architectural Technologies, and what it actually is trying to reflect is my motivation for the work that we do in the lab that is centered around the intention of enabling more technology used in architecture. So using new types of hardware, software, just being in touch with new developments and implementing those in architecture so that we can hopefully address the most pressing crisis that we see in the architecture and construction industry. So unlike the project that I will present later, a lot of my lab's work revolves around the use of robotics as existing hardware and how we can apply such a tool in architecture. And in this presentation, I'll use the term robot as a placeholder in a way for other technologies too. So we don't only look at robots, we also look at algorithms, which is where the project will come in. but I'll show you a little bit where other projects started and the motivation behind them. So if we actually look at robots, what happened is that they were developed for a different industry, in this case, manufacturing, and they're usually implemented to automate existing tasks and to replace humans, to make the human work faster, cheaper. And while this trend has been taken on into construction as well, and as early as the 60s, this is an example of a first kind of robot. Well, it's in a way a robot. Arguably, it's still human actuated, but it was developed for automating bricklaying processes. We think that there is a lot more potential in architecture if we use robots and hence other technologies to increase the possibilities for design and construction rather than to automate existing processes that are done by humans. So for example, by producing new material systems for very lightweight construction through differentiated form, and by generating and articulating space through new formal possibilities that result from both software and hardware. So at my lab, we're really interested in the relationship between designer and technology and between human and machine, and really how we can use technology that comes from other disciplines to make more enjoyable, maybe in a way, architectural spaces, to increase the quality of architectural spaces. Which is, I believe, where also the motivation for this project came from, on how can we use our expertise to make the current reality more enjoyable in a way from an architectural perspective. So I'd like to show just two projects. I'll go quickly through them. Just to unfold to showcase the potential that we see in using new technology in our built environment. And I'll start with a project that's focused around the use of multiple robotic arms for the assembly of differentiated space frame structures. This was actually my PhD project not too long ago. But I'd like to take you through how we normally think through such projects, also specifically as architects. So not necessarily as roboticists or computer scientists, how we approach these projects. So the goal here was to use the precision of the machines together with their capacity of working cooperatively to be able to construct complex space frames without any scaffold or additional support structures, as opposed to the regular ones that we see employed vastly and that have been extensively built throughout the past century. So while the construction method of the project was pretty straightforward, I used two robots to alternate the placement of elements so that one robot can constantly act as a support while the other one brings a new element. The implications on geometry, material, structure, and thus design, they resulted in very complex dependencies between the different parameters, which are really not possible to intuitively address. So traditionally, one could imagine the work of an architect as an intuitive process where you design a shape and then figure out how to make it happen. When we get into these types of technologies, the complexities of the interdependencies of all the factors, it just becomes way too high for us to intuitively deal with. So that's where we really have to revert to computational tools to help us really work, be able to design things that we're not able to do intuitively. So the types of problems that we address in such a project, they range from solving complex geometric configurations. Here, every bar is computed and placed to be tangent to two already placed bars to generate a stable node. To human-robot collaboration aimed at distributing tasks between the different agents. So here the human executes the welding, which is a more complex spatial movement, while the robot is used for its precision when holding bars in space, which is something that humans are really bad at. And going to including robotic constraints such as reachability and collision-free path planning into the design and planning process of such structures, which finally enables us to build full-scale structures that demonstrate the potential of digital fabrication techniques and computational design for the expansion of design possibilities. I'll let this quickly run to the end, just to take you through the workflow that we normally do in such a project. So we really work with full-scale structures and architectural interventions as much as possible. These result in sometimes pretty massive structures that we really use to test our research with. So our aim is really to tackle current design challenges by integrating as much information as possible into the design and construction process. I'll show one more project which we recently finished, which was focused at utilizing the robots in a similar way as the project I just showed, but for the construction of heavy brick wall structures. Again, without using any additional form or false work, which we then demonstrated through a full-scale glass vault that was exhibited in London early last year, right before the pandemic happened. So again, we're not using robots to automate an existing process, but to increase the design and construction space of possibilities, in this case by alternating the robot use between support and placement again, and assembling an arch without any external support. In order to build the entire vault, we built up on this procedure that builds an arch as a backbone, and then the robots individually built towards the outside of the structure to finalize the vault. So again, the project required us to combine different expertise, different knowledge, from structural form finding to robotic constraints, such as the overlapping reach volume of the two robots, with then patterning and sequence definition to ensure stability during construction, to successfully build the vault prototype as part of the exhibition in London. And I have a very short video, well, not so short, showing the process, which I'd like to run. I might stop it a bit early to save some time, but I'll just start it. So I took a little bit of a detour from the topic that we're going to discuss today, but I think the main point where as Corina said, we got together. We thought this would really make sense, as my lab works a lot on direct physical prototypes. We make large scale installations, so we really have the opportunity to make an impact, to make a physical installation that we can test in real life, and combining that with expertise in how in collective behavior, we thought is really the perfect match to move this project forward. I do want to jump over a few slides which were from a few other projects, just to save on time a little bit. So yeah, that will take me to our project, Bringing Social Distancing to Light. And the project really started out of a wish to contribute with our research to the many challenges that the pandemic has brought upon us. And honestly, it grew out of a brainstorming session that we had in the lab, where we asked where can our expertise and our pretty unique position as architects and fabricators be useful to the current crisis. The project is currently being developed actively at the Create Lab by Eric Duong, who is a researcher who joined the team as a research specialist specifically for the development of this project, and Lauren Dreyer, who is actively a PhD student at the lab. And Eric is also here today, and he's in the panel to take on any questions on the technical details of the project. So you'll get to see him later, hopefully. Yeah, as architects, we could not notice how our public spaces were slowly turning into these types of images with hard boundaries, confining people in their freedom of movement, and floors that are plastered in the same types of stickers everywhere. And particularly, stickers have many drawbacks. They only work for situations in which people are stationary, such as queuing, sitting, or waiting. And they're not adjustable to any changes. Whether there are few or many people in the space, they're going to do the same thing. Whether requirements become looser or not, they just they don't lend themselves for adjustability. So while these measures were absolutely necessary, we asked ourselves if there is a smarter way to address the need for social distancing, but to improve rather than diminish the quality of a space and the experience that people have in architectural spaces. So the approach that we developed uses digital media and computation for a dynamic visualization that follows pedestrians and informs them on safe paths. This way, we generate a system that is dynamic and informative, but hopefully even playful and engaging, so that occupants are not feeling forced or contained, but that they rather feel as part of a larger interactive system that they can enjoy. The project draws inspiration from a set of precedents, mostly from the art world, in which projections or other means are used in interaction with humans. Hansel and Gretel is such a project. It is an interactive media installation that uses a similar approach in terms of technology as we do, uses overhead cameras that augment what they see and project back down to the floor. They use projection to achieve a different effect than what we do in order to achieve total immersion in the space and the experience. But regardless, it shows the potential of the medium to change an otherwise empty space into an interactive environment. Another project, Smart Distancing System. This is the closest to our own proposal. However, it is not an informed system. It solely visualizes an animated bubble around people and groups of people, but it does not offer any additional functionality in terms of flow management. And the last project, Smart Artifacts Mediating Social Viscosity, it's a project that doesn't utilize projection, but it is relevant for our study of movement and pedestrian flow. Salamanca is interested in the idea of social viscosity, or the resistances in the flow of people moving, and how to reduce this viscosity through smart artifacts or signals, so through interventions directly in the spaces. They look specifically at crosswalks, and they develop a conceptual system that analyzes factors like movement speed, group size, to suggest paths of least resistance. So in relation to our project, this really sets a precedent of regulating flow through interactive visual systems. So what does our project actually do? Simply put, we wanted to develop and employ a smart projector. That's what we called it, that can inform pedestrians on safe paths. And we limit ourselves to public indoor spaces, specifically because they offer the possibility to attach projectors to ceilings, and because they are in a controlled environment that we can work in easier. In a schematic way, it can look something like this. It identifies a safe region and the path, and it suggests a direction of walking for pedestrians. The setup of the project consists of a projector. We have settled for a high brightness, short throw projector. We use a board, currently using a Jetson Nano due to its greater computational power than a Raspberry Pi, for example, and a camera that is attached to it, in this case, a wide-angle Raspberry Pi camera module. The system is modular, so that it can be adjusted to different spatial requirements by simply reconfiguring the projectors as needed. And as to the technical challenges and implementation, we broke up the entire process into 3 steps. So first, we need a system that can accurately detect people from the camera input, of course. We then need to be able to track individual agents to compute their movement direction. And in the last step, we need a visualization strategy that is then projected onto the floor. And then we combined all of these in a common process, which involved mapping the projector area to the camera area and using the 2 in tandem. This is Eric doing very first detection test at home, since we're all working from home, but we got back into the lab. So for the detection process, we opted for a deep learning based approach, since this allows us to deploy the projector and camera in as many different types of spaces as possible while still being accurate in detecting people. This, of course, comes with a trade-off in efficiency. And with our still limited computational power, we needed to use a detection network that would be fast and accurate. We settled on MobileNet SSD, single-shot detector, which was developed specifically for mobile devices, so very similar to our own setup. And it presented a good trade-off between speed and accuracy. And we found that with TensorRT optimizations on the Nano, it could run in real time. So pretty much what we needed to get. For the visualization, which is based around identifying a pedestrian's movement and orientation, we built in tracking alongside with the detection. This was done with a proximity heuristic. In the following way, new detections are assigned a fixed ID, and if they are not detected in the frame within a certain amount of time, they're being deleted. We also use the tracking as a correlation tracker, because using deep learning as a pedestrian detector is relatively expensive computationally. It is more efficient to instead spread out the use of the detector and use a more efficient but less precise method in between. The correlation tracker itself uses visual information from prior frames and the current frame to then determine the location of the object in the current frame. For the visualization perception, it is really important to not have sudden jumps in there, but rather smooth transitions between the movements. The Jetson Nano is not really capable of computing the location of a person at a frame rate that would show continuous movement. So you can see it on the left, what it looks like normally jumping around. And because we also use a bounding box to compute the center point of a pedestrian, so that changes with any sort of local movement, even if you don't walk around. All of this leads to a good amount of noise in the signal, and to address this, we use Kalman Filters, which is a method commonly used in navigation and other coordinate-based systems to smooth out the noise. And hopefully you saw that on the right side, the green dot is a lot smoother than on the left side. One very important point for us from the very beginning was data privacy. As a result, we make sure that no personally identifiable information from the camera use is ever collected or stored throughout the project. Instead, the video data from the camera is used for people detection and tracking before being translated to Cartesian coordinates. Only these coordinates are then used for the behavior model and for the light projection. So all computing happens locally on the board, where in each frame we evaluate it, we extract the coordinates and store them, after which the frame itself is being discarded immediately, so that we only end up with points in space and no information that could be traced back to any individuals. And the last point that we're working on is the visualization itself, which is the main part of, or really key to the project. We need the visual representation of the paths to be very simple, understandable, and adaptable to as many spaces as possible. So we started by looking at multiple types of visualizations and testing them out. Early ideas included a dynamically generated line trail for pedestrians to follow, and other graphics that highlighted the path, so which way you should walk. But we felt that these were still too prescriptive. We wanted to get away from the arrows and signs that dictate exactly where people should be or how they should move. And even with a line that can adjust your movement, we felt it still feels too limiting, like you were not allowed to deviate from that path. Other ideas that we looked at use repeated lines or particles to suggest spaces where occupants could move, rather than a specific trajectory. These were more in the spirit of what we wanted to create, but we decided against this system too, because they're often information overload, and it can be difficult to decipher where to go. So currently we settled on what we call a compass system, which uses color and directionality as a soft signal of an ideal path. The calculation of the direction right now simply relies on path location data and what it projects forward to determine a destination and the path. This is one topic that we're actively working on, and hopefully we'll be able to take this further. Ideally, we would use an agent-based model that is based on a physical space that would run thousands of simulations using a good social behavior model, something like social force model, and train another machine learning model to make predictions based on that to guide people to move safely. And this is an example of what the visualization currently looks like. So the color and the length of the lines indicate the more dangerous direction or the safer direction, but while still keeping it a soft indication and not something that feels too confining. We are, however, still working on potential visualization strategies, particularly since we want the system to be adaptive to different contexts, different interiors, different spaces. So we provide this opportunity to adjust the actual looks of it to match the space that we work in. And this has been pretty helpful also right now with our current partners. So this is really where we are right now in our lab at Princeton, trying to match all of these things together. Facing a bunch of challenges that come from real-world implementations. These are only very initial tests and by no means fully functional, but we tried to capture what the system could look like when employed in a real-world scenario. So you might notice it's a bit dark in the lab, which is Also, due to one of the main technical challenges that we have, we're still testing projectors and had to find out that we really need the most powerful ones. So these videos are still taken with a less powerful projector, and then work in the dark. We aim to use the system in daylight situations, so not just in the dark. And this is just another shot of Lauren and Eric testing it out so far. And yes, the next steps, we want to move out of the lab. We have partnered with 2 library spaces that allowed us to set up our system in a real world environment. On the one hand, the Trenton Public Library, where we will use the entrance area around the circulation desk, since it did prove to be the most challenging area in terms of pedestrian traffic. And on the other, the Princeton Public Library, which is right around the corner from us, where similarly we identified the area around the circulation desk to be the most interesting and challenging one. And we're hoping to have our installation up soon and also use it as a means to gather data on how the space is being used over time, and ideally on how efficient our system is, how it's actually functioning. So to wrap up, these are the points that we're currently looking at: testing higher brightness projectors in daylight, testing our entire system in our lab to make it functional and robust, and then setting it up in the library spaces, monitoring and collecting data over the summer. Future research ideas, there's many we would love to look at. Just like with any research project, it doesn't stop when you want it to stop, or when you plan to stop. We would like to address more specific situations such as queuing or gathering, which requires a different approach than the movement situations. We want to interpret the data from the library use for long-term space adjustments. We want to evaluate the efficacy of our system using the 2 case studies, and we are thinking of potential uses of our system outside of pandemic situations. And I will stop here. Thank you very much.
Thank you so much. So I'm going to start off with some questions that I've received, and then hopefully the audience will submit some more. Okay, so the first question I got is, how do you see the system being adapted to different types of public spaces, transit, venues, cultural institutions, for example?
Yeah, thanks for that. We thought a lot about what possible spaces we would want to employ it in, and initially we thought a lot about spaces like stations, train stations, metro stations, where really the people flow is extremely crucial, and particularly in the pandemic situation. We think that it is pretty adjustable to different scenarios. The main thing being identifying the geometry of the space, the locations of the projectors and cameras, and how different sets of the hardware can be matched together so that we can cover an area with a different geometry, which is what our system allows. And on the other hand, so there's actually 2 more points. The visualization itself can and should be adjusted to match, say, the use. If it's a space where people walk really, really fast, it can be very helpful to have a much more present visualization. If you want to slow down people, maybe you can use visual tools to do that in the visualization. And the other point is one that I mentioned at the very end. We are now looking only at people in movement, but there's definitely specific situations such as queuing, or in a train station situation where people come out and other people have to get in, that have very specific constraints that we would need to model and address and identify what would be an ideal type of movement there, rather than just when we move from A to B, what we're looking at now.
Okay, so here's a follow-up question. What can we learn from this projection system that might translate to newly constructed spaces or change existing public spaces?
Yeah, that's also something we thought about a lot, and initially we would have loved to make this project encompass all of it, just make it way bigger than we could handle. But I think this would be a natural next step. That's very interesting to us. So what we are hoping to learn is get data on how spaces are being used. We will be able to tell how often do people say breach with these distancing requirements, or when are certain spaces used a lot or less? How do the people actually move in the space? I think we don't have a really good overview of that yet right now. So wherever we would install it, we would be able to capture that data. And we definitely think there's things to learn out of also how efficient our system is in terms of how we can move furniture around or mobile things around spaces, but also what sort of requirements do spaces have nowadays as opposed to before a pandemic situation. So we'll be able to tell if, say, a certain door entrance where you go through is the key area where our system will constantly have to like negotiate, and where it might struggle with, that this is something we might want to plan differently in the future. Say you need to make a much wider space. I mean, this is very direct, but we're hoping to identify different scenarios that are not, say, as intuitive as that example.
Okay, thank you. I've got a now a question for
Maybe Eric,
Corina.
No? Okay.
The question is, compare the pattern of social distancing circles that Stefana showed on that lawn to the termite pattern that you showed at the landscape scale. Can you say something about how they're different, how they're the same? What do you learn about this?
Yeah, thanks. And I think it actually combines really well with a question in the Q&A that was just asked that I'm going to read, if that's okay, just to kind of merge the two.
Yes.
Thanks for the interesting presentation. Learning from nature is surely a smart thing to do. I hear about biomimetics. Does your area of study fall within such space? Are you able to point us to a database of things people are doing to learn from nature? So that's a really interesting question. I mean, that's partly how Stefana and I started to talk about this. So yes, there are ample areas where people are trying to learn from nature. I'm not sure that there is actually a database. I should look into that. But here's an example that's very popular at the moment is natural systems are able to do things without without someone telling them what to do, right? So for instance, termites or ants will build this very sophisticated architecture without actually being given a blueprint, without someone telling them, this is what you're supposed to do today, here's how you're supposed to build that, you can stop now, you can go elsewhere, right? They do that themselves. It's self-organized, right? So one big area of robotics has to do actually with building robots that can self-organize without having someone that tells them when to go where, when they're done doing this work and they should start another part of the work, and so on and so forth. And tying a bit back to the other question, so I was really struck actually by the lawn photo that Stefana showed. I hadn't actually seen that photo myself, but I don't know if you noticed the circles, that they looked actually very similar indeed with the termite mounds. They seem like they are, they're clearly forming some sort of regular pattern. But there's one key difference, and this seems to be a fundamental difference between natural systems, how they self-organize and what patterns emerge, and how we build systems. We tend to love 90 degrees angles for some reason. And so if you look at that photo, they were definitely a grid, right? Whereas if you look at the termites, the angles between, if you try to draw the same lattice, the angles are 60 degrees. It's most often natural systems self-organized into triangular or hexagonal patterns, whereas we tend to like things that are, it's possible because it's easier to navigate, because it was easier to navigate in the past, and therefore we kind of like are stuck with that way of building cities and roads and everything. But there is something to be said about why do natural systems. So in some sense, the termite mounds what they were doing for these other animals is that they are socially distancing them. The animals don't have to compete for resources. They are naturally socially distancing the antelopes and the zebras and everyone else. And I think part of the question, this ties back to the question about the building new spaces, is how do we build in some of these ideas and some of the natural kind of signatures of patterns in natural systems, and might that actually allow us to fit more people in the same space, and to allow, it might not be easy, in terms of navigating agricultural fields, but it might be easier, for other questions that we're trying to ask. So yeah, I think that there's a really ripe, this is a really ripe moment for cross-pollination between these fields.
So I have one more question that was sent, which is, I think you've already, to some extent, both of you sort of talked about this, but I just wonder if you want to elaborate the role of robotics and research in robotics and how it would connect to what you're doing in your project. How could it enhance or change the outcome?
I can jump onto this. I mean, a lot of my work revolves strongly around robotics, and this is maybe one of the few projects that doesn't employ robotics right now. But we were talking and thinking about, what if the system wasn't stationary and it's not something you just plug onto your ceiling and hope that it works, but if you combine it with the potential of mobile, of movement, which is basically what we take advantage of robotics from the perspective of movement, so the fact that things can move around. And I think any sort of intervention can actually gain from that. It's basically giving us another degree of freedom. And as opposed to just thinking about a static system where we design a space, we build it, and there it is. Adding movement onto it, I think, can help a lot. So yeah, we were playing around with ideas of like, could these be little machines that drive around and project or show you, or maybe they're moving around ceilings to cover larger areas, reorienting things. It's basically giving us more freedom, and I think that's crucial to rethinking architecture a little bit from this very static thing that it might have used to be, to something more dynamic.
Okay, I hate to do it, but there's one more question, and that will have to be it because we're basically at the end. How do you see the future of research in terms of solving human problems? Okay, go for it. That's a nice, simple question.
Yeah. Corina, do you have any very... I'm just gonna throw it over.
Sure. Wow, that is a... Look, I think that there is more and more interdisciplinarity actually happening, and I think nothing like COVID to show us how interdependent we are on each other and how much we need each other to kind of operate simultaneously, and many people from different fields thinking together about the same problems, right? So I think my whole branch of the field is basically relies on kind of like serendipitously running into other people, thinking about problems in different ways, kind of like the interaction with Stefana, and then trying to see, can we come up with something together? And I think there will be definitely more and more of that, and we're seeing certainly importing ideas from biology has been, increasingly the case, going into everything from trying to build self-organizing robots to trying to find a solution for the political polarization that we're now in, and so I do think that there's we need to do that. We must do that. We more so than we have, and truly interdisciplinarily, not just kind of working side by side, but really reaching across and kind of learning the same language so that we can really do it productively.
Well, thank you both so very much. And I wish we had longer, but this was a great presentation, and it was just so stimulating. So with that, C3AI DTI thanks you and our visitors, and look forward to seeing you at the next time.
Thank you very much.
Thank you. Thank you very much.